Good afternoon. My name is Jean-Louis Briaud. I'm a professor in the Department of Civil Engineering and holder of the Buchanan Chair at Texas A&M University. This is the 13th Buchanan Lecture, and I look forward each year to this event. It's a lot of work, and it tends to remind me how fast the years go by, but it does feel to me like the Thanksgiving of Texas Geotech. You know, the family is coming home. It plain feels good. I want to start the afternoon by recognizing a special person who's been a great supporter of our program over many years. He's always there when you need him. Actually, I believe that he has attended all the Buchanan lectures since 1993. I'm talking about Doug Flatt. Doug, thank you for your support, your generosity, and your friendship. Please stand up. Now let me talk a bit about the Buchanan Conference. You know that we've enlarged this concept of the Buchanan Lecture since 2003 with this Buchanan Conference. The conference starts on Friday morning and finishes on Saturday at noon. This morning, selected students heard the presentations on geotechnical engineering and the value of graduate studies. Jean Audibert, Ken Tand, George Cozart, Harry Poulos, Tom O'Rourke all shared their thoughts on the topic. Tomorrow morning, we'll have a presentation on our program by the Texas A&M University Geotech faculty, followed by the Geo Magic Show with Cassie Rutherford as Grand Wizard. One more note about those who continue to support our program financially and otherwise. The university is very grateful, I can assure you. Your generosity is very much appreciated. You may be interested in knowing that this university's budget is about $1 billion a year, and that 10% of this budget comes from gifts, $100 million each year. Without your generosity, the tuition at A&M University would be 33% higher. Your input, comments, and guidance is always welcome. If you see something we can improve, please tell me. If you see something you really like, please tell others. Now let me take advantage of the situation to mention that we will be teaching the Geotechnical Engineering Case Histories course this spring. If, as a consultant, you wish to contribute by presenting one of your case histories to the students in the spring, please let me know. A bit of administration details. We no longer advertise the Buchanan Lecture by a brochure in the mail, and I'm debating whether we shouldn't start that over again. I'm worried that I'm not reaching everyone that wishes to know about this lecture. So please raise your hand if you wish to see a hard mailing go out and with a brochure sent to you. A few hands. We'll consider this, and we would use the Geo-Institute mailing list for that purpose. We'll still send emails as well. If you wish to receive an email and you haven't for some reason, please sign the guest book, and the guest book will be circulating during the afternoon. You may also check the website listed on the cover of the Buchanan Lecture booklet that you've picked up in the front. The 2006 Buchanan Lecture, next year's lecture, will be posted on that site in the middle of the summer 2006. All right, here's the program for this afternoon. First, Professor David Rozovsky, head of our Civil Engineering Department, will say a few words about the state of the department. Second, I will ask Professor Steve Wright, president of the Geo-Institute of ASCE, to share some thoughts about his vision for the coming year. Third, I will invite Mr. George Cozart, Senior Vice President of Terracom, to come and give the Terracom Fellowship to the graduate student who was selected to be the first recipient of this honor. Terracom made a generous gift, let me rephrase, a very generous gift, to Texas A&M University to fund the fellowship to support a graduate student in geotechnical or environmental engineering. After Mr. Cozart, Professor Tanner Blackburn, who joined our geotechnical faculty in September, will come and introduce Professor Poulos, who will follow with his Terzaghi Lecture. After a discussion period, I'll have the pleasure of introducing Professor Tom O'Rourke, who will follow with the delivery of the 13th Spencer J. Buchanan Lecture. A discussion period will follow, and then Dr. Philip Buchanan will thank Professor O'Rourke and give him the plaque. After a few photos, we'll reconvene for a reception at my home. Maps, everybody is invited. My wife knows about it. Maps on how to get there are at the entrance. Now let me call on Professor Rozowski to say a few words about our department. David has been here only 1 year, but has already accomplished quite a bit in little time. David?
Good afternoon. Thanks very much for inviting me to say a few words. I really like what Dr. Briaud said, is that I'll get up and say a few words about the state of the department. Here you go. The state of the department's really good. Things are very good at A&M, and things are even better in the College of Engineering, and a tick better than that in the Department of Civil Engineering. Let me add my welcome to all of you, especially our guests to Texas A&M University. We cooled the weather down a little bit. It's about 10 degrees below normal for this time of year, which is something I cherish as a relatively newcomer to this area. This is an exciting time at A&M and a very exciting time for our department. If you don't know, the Department of Civil Engineering at A&M is the largest in the country. We have about 1,100 undergraduate students. We have about 350 graduate students. We have close to 60 full-time faculty, and we're growing. Among the highlights this past year, we completed the naming of our department. We're now officially the Zachry Department of Civil Engineering, with great thanks to the Zachry Foundation and Bartel Zachry and his family. We added 4 new faculty this year, 1 in smart structures, 1 in environmental biotechnology, 1 in risk-based project management, and of course Dr. Blackburn in geotechnical engineering. We're adding 6 new faculty this coming year. We're looking for folks in transportation systems and random vibrations, construction engineering, environmental engineering, coastal engineering, and advanced civil engineering materials. That's 10 new faculty in 2 years. After that, we have plans to add 6 new faculty in the 2 years that follow. So we'll be up close to 70 faculty, which is really quite a remarkable department. Just because we're the biggest doesn't mean we're the best, but we certainly have the opportunity to do great things in all of the major areas in civil engineering, and that's really what we're trying to do. Department went up in the rankings this past year. We're now ranked 6th among public institutions at the undergraduate level. We're ranked 8th among graduate institutions, public institutions again. So basically, we're solidly ensconced in the top 10. Puts us in some very, very good company, and it's something that we all take great pride in and continue to work to improve in the year ahead. Another big piece of information that we just compiled and found, that our research is up 30% from last year and 75% from the year prior. We did about $10 million in extramural sponsored research this year. It's a tremendous department. We welcome groups such as yours, such as the Buchanan Conference, to our campus, and we hope you like what you see. We hope you have a chance to get over to the main part of campus, because you're sort of on one of the commercial rows out here, and visit with us. Come see the department. Come see the 5 buildings that make up the department. Walk around the College of Engineering. Spend some time meeting some of the Aggie students. They're a tremendous group. Hope you like what you see. For those of you that are guests to this campus, and we hope that you apply to A&M for graduate school, we'd sure love to have your application here. We have very competitive assistantships. We have increasingly competitive fellowships. We're really going after the very best students in the country, and we're having some great success, and we'd love to count you among them. A&M Civil Engineering has got a very rich, very proud heritage, some of which you'll hear about during the conference, some of which you'll see when you walk around campus. We enjoy a special place in the college, and we enjoy a special place in the university. And that's because we are very highly regarded on this campus as a real scholarship department, a very functioning, very productive department that trains students that are work ready at the onset. A lot of departments, my colleagues around the country will bear this out, a lot of departments of civil engineering going through a little bit of a transition. They're trying to redefine themselves, or even struggling a little bit as departments of bioengineering and computer science and electrical engineering and advanced materials and so forth sort of have the dean's attention and the president's attention, the provost's attention. Civil engineering is very strong in the state of Texas, and we have a tremendous position on this campus as a very, very strong department. In fact, we're one of 2 departments in the College of Engineering that improved in the rankings this past year. So I think this is a great department. I think we're on an exciting vector. I think we've got tremendous proven ability to hire great faculty and recruit great graduate students. We're consistently adding talent to this department, to our intellectual capital, if you will. I hope you look around while you're here. I hope you like what you see. If you have questions, any of the faculty and graduate students here, undergraduate students, would be happy to answer them for you. Welcome to A&M, and I hope that you have a great conference.
Greetings. It's a pleasure being here. As president of the Geo-Institute, and then prior to that as a board member of the Geo-Institute, I've had a lot of opportunity the past several years of traveling around and attending various regional geotechnical events. I think probably one of the most prominent ones, or soon becoming that, is the Buchanan Lecture. It's certainly recognized as one of the top regional geotechnical events that we have. I believe the Buchanan Lecture, if it's not the first, is certainly one of the first named regional lectures that we have in geotechnical engineering. I think a lot of the success of the Buchanan Lecture, I'm sure it's due to many people's efforts, but I think Jean-Louis Briaud is largely responsible for the success that we've seen in the Briaud Lecture. And I'd like you to join me now, and you'll probably have opportunities later as well, to give Jean-Louis a round of applause for all that he's done in bringing the Buchanan Lecture to where it is today. Now, Jean-Louis asked me to talk some about the Geo-Institute. He told me I couldn't talk about football. First of all, I would like to recognize the students in the audience and the large number of students. I don't think I've attended a geotechnical event in the United States where there's such a large number of students. Can we just again, can all the students stand up? I think half or more of the audience is students, and that's commendable because that's important to the geotech. And you can all sit down now. This is extremely important to the Geo-Institute because this is really where our future lies, is in young people, and it's nice to see that they have opportunities like the Buchanan Lecture to get involved, and hopefully we'll continue that involvement in the Geo-Institute into the future. I attended the Canadian Geotechnical Conference recently, and that conference also had well over half of the attendees were students. And so I think it's encouraging to us that have been in the profession, like myself for many years, that there's so many young people that are getting involved in the profession, and I think the future is very bright. One of the things that I think probably most of you would like to hear about is not what my vision is about what we're going to do for you and might do for you, but you're interested in what does the Geo-Institute currently do for you. And I think there are a number of services that we provide, hopefully, to our members and you take advantage of. Certainly our conferences are one type of event. Also the numerous technical publications that we have. We now have 2 journals rather than just a single journal. We have the Journal of Geotechnical and Geoenvironmental Engineering, along with the recently added International Journal for Geomechanics. I would, in concluding my remarks, like to invite all of you to 2 of our upcoming conferences that will be held this spring. The first of these is Geo-Congress 2006. It's in Atlanta. It will be February 26th through March 1st. It's got an outstanding program. Included in that program will be the Terzaghi Lecture, the Seed Lecture, and the Peck Lecture. which are the top 3 lectures that the Geo-Institute puts on. Also, following that, a month later would be the 4th International Conference on Unsaturated Soils. I know that many of you, probably most of the practitioners here, practice in the state of Texas, and you can certainly appreciate the importance of unsaturated soils. The international conference will be held in Phoenix, Arizona in the first week of April, and I would encourage you all to attend that again. I'm just curious, how many of you are members of the Geo-Institute? Let me see a show of hands. Yeah, I think most of the practitioners. Some of you practitioners may be members. A recent survey of our members where we asked them if they were people in ASCE, if they were members of the Geo-Institute. A number of people indicated they weren't, but they were in fact members. All you have to do to be a member of the Geo-Institute, if you're a member of ASCE, is check the box on your dues form. It doesn't cost you any more money. So I would certainly encourage all of you that are ASCE members to also be sure that you indicate an interest in membership in the Geo-Institute. And again, John Louis, it's a pleasure being here. Thanks for inviting me, and I hope you all have a good time.
Howdy. Many of you have been major players in the Texas A&M Civil Engineering Department for many years, and many have contributed in many, many ways. Terracon is honored to join that group today, and by endowing a fellowship to Texas A&M University. Terracon endowed the first Terracon fellowship to Iowa State, because that's where our founder went to school. We don't actually have very many graduate students from Iowa State, but I guess we had one real good one. We held a competition in the company to nominate the next university, and I guess our thought is that if we can keep this going perpetually, endowing us a fellowship every 4 to 5 years, hopefully we can make some progress in helping to the universities to strengthen their graduate programs in geotechnical engineering. Once we started this process, we got a lot of support from the university. When they found out that it was a competition, I think they got really excited. And David Rozowski, Don Murph, John Louis, and John Small with the foundation gave me all the support I needed to present to the Terracon board so that they would make the right choice. And I do want to thank the Terracon board for that generous gift. Texas A&M was picked for the quality of their program and their success of their former students who play such a vital part in our company and companies across the United States. I'm pleased to award today the first Terracon Fellowship to Evan Garish. Evan, come on up.
Thank you so much.
Evan's a first year, I guess, graduate student from Portland, Oregon.
Yep.
Right? And we're looking forward for him doing great things. Thanks, Evan.
I'd also like to add that Evan's a heck of a TA. He's helping out our undergraduate geotechnical course this semester and doing a great job. So thank you, Evan. I'd like to introduce Dr. Harry Poulos. He joined the Department of Civil Engineering at Sydney University in 1965 and was appointed full professor in 1982, a position which he held until 2001. In 1989, he joined consulting firm Coffee Partners International and is currently a senior principal and chairman of the technical development with Coffee Geosciences. He is also an emeritus professor at University of Sydney and adjunct professor at Hong Kong University of Science and Technology. He has published several books and technical papers on foundation settlements, pile foundations, and offshore geotechnics, and has also been involved in over 300 major projects throughout the world. He is a fellow of the Australian Academy of Science and the Australian Academy of Technical Sciences and Engineering, a fellow of the American Society of Civil Engineers, and an honorary fellow of the Institution of Engineers, Australia. He is an appointed board member of the International Society of Soil Mechanics and Geotechnical Engineering for the period of 2001 to 2005. In 1993, he was made a member of the Order of Australia for his services to engineering, and in 2003, he was awarded a centenary medal by the Australian government for his services in science and geotechnical engineering. He was selected as the Australian Civil Engineer of the Year for 2003 by the Institution of Engineers Australia, and as the inaugural Geotechnical Practitioner of the Year by the Australian Geomechanics Society. So will you help me welcome Dr. Harry Poulos as he gives his 2004 Terzaghi Lecture, Pile Behavior and Consequences of Geological Construction Imperfection.
Well, thank you very much, Tanner, and ladies and gentlemen, it is indeed a great pleasure to be here to represent this 2004 Terzaghi Lecture, which I was extremely honoured and gratified to be awarded. And as you'll see, I'm going to talk about imperfections in terms of the consequences of those imperfections to pile behaviour. When I was primarily an academic, I had the luxury of dealing with ideal situations, and I was able to idealise the soil and pile, and you find out a lot about pile behaviour by examining the ideal situation. However, when I became primarily a consultant, the realities of life are much harsher than the perfections of modelling in a university environment. And so I thought it would be useful to try and collect together some information, some experience on how imperfections of various types influence pile behaviour. So what I'm going to talk about firstly is the sources of imperfection, fairly briefly. Also very briefly, say something about the analysis of pile-soil interaction and how we arrive at some of the conclusions that I'll present to you. Then I'll talk about the effects of geological and natural imperfections, and then the effects of construction imperfections, and finally, how we cope with the consequences of those imperfections. Now, normally, we like to define what we're talking about, and so when I looked in the dictionary at some entries related to imperfection, I found these: fault, defect, flaw, weak point, discontinuity, break, fracture, fissure, crack, gap, and even seamy-side. Now, all of these, interestingly, have both a sociological and an engineering implication, even the seamy-side. And in fact, what I'm going to talk about is subtly but nicely summarized in this extract of a poem called Imperfection by the Russian poet Georgy Konstantinov, who says, if a building collapses in ruins, what does it matter that it was built after a talented plan? And I guess translating that to pile design, what it's saying is that no matter how brilliant your design is, if you make the wrong assumptions, then your building may well collapse in ruins. And that, of course, is what we want to avoid. This slide shows rather nicely the process of idealization that we as engineers have to go through. And it's a slide that I got from Professor Goran Salfors of Sweden. And the situation is here that we have what we want to build, a building here, and we've decided it has to be on piles. And we, of course, do some investigation, and then we idealize the situation. And we look at the model of the structure, we look at the model of the foundation, we look at the model of the stratigraphy of the soil, the geology. And then, of course, we input into our mathematical model material properties that we have assessed, and we come out with a prediction of behaviour. So this whole process of prediction involves a number of fairly critical steps. And what I'm really talking about today is this component of the system, the idealization of the model, and in particular, how we model the piles and how we model the soil. That is a major problem. And in developing the schematic model, obviously the first thing we have to do is to represent the site geology, and then we have to simplify it to represent the stratigraphy as best we can, because obviously we can't, in a practical sense, include every element of the real site geology. Then a major component of that is to assign geotechnical and structural parameters to the problem, and then to consider some of the realities, the fact that soil behaviour is non-linear, also pile behaviour is non-linear, that the soil, rather than being a homogeneous isotropic elastic half space, is actually a layered non-elastic material. And of course we also have the possibility that loading of our foundation system may occur not only because of the weight of the structure and the forces on the structure, but also due to the fact that the surrounding ground may move. And I think Professor O'Rourke will be talking more about that in his lecture later on. The sources of imperfection that I'm going to look at arise from three major sources. Natural geological sources, firstly, then secondly, inadequate investigation, and thirdly, imperfections related to construction. And Terzaghi, of course, has a quote that tells us that the earth in its natural state is never uniform. Unfortunately, in practice, clear and simple soil conditions are rather uncommon. And yet, unfortunately, in much of our practice, we assume clear and simple soil conditions. And there are many situations, I'm sure many of you would realise, where the conditions are certainly not simple and clear. This is the geological origin of some deposits in southern Sweden, where you see that the idealisation of this particular formation as a homogeneous semi-infinite isotropic elastic half space would be somewhat imperfect. And just to give you another indication, here's some geological formations in Greece. Again, the same sort of problem, but we have the harsh realities of real geology do make some of our simplifying assumptions rather tenuous. Inadequate investigation is always a problem, and particularly in these days where we find that clients are, for some inexplicable reason, wanting to try and save pennies on what I consider to be the most hazardous element in their project, which is the ground. And so you get a typical situation where you put down two boreholes like this, and you hit a stiff stratum, and then optimistically you say, well, that defines our stratum. We have a horizontal stratum of soil, and then we have good stiff material below. And in fact, nature, unfortunately, in this particular case has a compressible layer below here. There's been an old riverbed here, so you have a depression in between the boreholes. And so basically, because you've done an insufficient number of boreholes, you have made inappropriate assumptions of the conditions between the boreholes, you haven't taken the boreholes deep enough, and you haven't used geological interpretation here, then you've got an inaccurate ground characterization. And again, Terzaghi has an appropriate quote. This comes from the Building Research Congress in 1951 in the UK. If the subsoil conditions have been misjudged, for example, on account of inadequate sampling operations, erroneous interpolation between boreholes, or lack of care in the examination of the soil samples, the difference between anticipated and real settlement can be distressingly important. And we'll have a look at that distressing importance in a little while. Construction-related imperfections, they can arise both from drill shafts and also from driven piles. Here's a couple of examples of driven piles, imperfections. In this particular case, which happens to come from just outside of Baltimore, I gather the situation was they were driving and wondering why they hadn't reached a set. And when they excavated the pile, they found, of course, that the pile had actually crushed like this. And this very famous diagram, many of you will have seen this before, in Sweden, pile driving on this side of the road, driving, why are we not reaching rock? And of course what had happened, this pile had actually, because it's an H pile, had turned around and was actually jacking this car up. So That's a pretty extreme example of imperfection, but compare this to what we assume in design, which is a vertical elastic member, and you'll see that this is anything but that. And then, of course, we have the all too common situation where we have drill shafts which are not integral. There are gaps in the concrete, there's exposed reinforcement and necking and so on, all sorts of difficulties if the pile is not constructed correctly. And yet, in our idealisation, in our design, we assume the pile to be a perfect elastic cylinder. Now, if we're going to examine the consequences of these types of imperfection, then we need to have some tools available to look at those consequences. And in what I'm going to show you, I've used 2 or 3 different tools, depending on the problem. The first tool I've adopted is finite element analysis, trying to look at mechanisms and capacity of the pile or the pile tip as appropriate. Secondly, I've used boundary element analyses of pile-soil interaction, which incorporate both nonlinear soil and pile behaviour, and also looking at the interaction between piles in a group through the soil. And associated with those analyses is the ability to incorporate what's called here free field soil movements. These are ground movements that will impinge on the pile from some external source. And with that latter type of analysis, there are basically 2 ways you can go. The first is that you can do a complete analysis where you model the pile, the soil, the loading and the source of ground movement all in one single analysis. And this gives you a complete solution, but it's often complex and time-consuming, and it's often difficult to get all parts of that modelling correct. And so I have preferred a 2-stage approach or a substructuring approach where we separately calculate the free field soil movements due to whatever the source of soil movements is. We then carry out a pile-soil interaction analysis using, for example, boundary element methods, and we find this to be generally a rapid and efficient way of doing the analysis, and one that is very suitable for parametric studies. So I'm now going to look at some geological sources of imperfection, and I'm going to look, in some cases rather quickly, at 4 sources of imperfection. The first is where we have clay seams present below the pile tip. So the pile goes through soil into rock, but in the rock there are clay seams, a not uncommon situation. The second is where we don't have horizontal layers, but we have layers of variable thickness and perhaps sloping bedrock. The third case, one that I alluded to before, situation where the piles are in fact founded in a stiff stratum, but there is a compressible stratum below, which will of course impact on the pile performance. And then finally, I'll look very briefly at a situation where we have boulders which may be encountered by a pile in a group, and what effect does that have? Well, taking the first one first, the issue of thin seams in bedrock, the analysis approach that has been taken here to examine this is that we've firstly done a finite element analysis to look at the effect of the clay seam on the pile tip behaviour. And we've done a parametric analysis, as I'll show you. The second thing is then that we do a complete analysis, a pile-soil interaction analysis of the whole pile. That's the shaft plus the base, incorporating what we've learned about the effect of the clay seam on the pile base or tip behaviour. And then finally, we look at the effects of interaction between a number of piles. I'm not going to go into great detail on that last issue, but let me start off with this basic problem. This represents the tip of a pile, and even though I'm looking at imperfections, it is of course idealised, but we have to make idealisations to get answers. So here's the pile tip. It's a rigid circular area of diameter d. Here is our rock, which then has this clay seam, which is about 1/100th as stiff and as strong as the surrounding rock, and that clay seam is of a thickness Ts and is at a distance Z sub S below the base of the pile tip. And if we do finite element analyses of this particular problem, we get some indication of mechanisms and also of the effect of that clay seam on the load settlement behaviour of the tip. Now, this first diagram is simply displacement patterns that come out of a finite element analysis, Plaxis in this case, when there is no clay seam here. So this is all rock. So basically this is the sort of pattern we would expect. The footing goes down, it pushes the soil up outside, and that's more or less what we expect. Now if our clay seam is here, and it's a rather extreme clay seam, very thick and very nasty, but now you see we've generated a rather different mechanism because the presence of the clay seam allows the soil to flow in a different manner to that of the homogeneous rock. And the consequences of that are quite significant. This is load, this is settlement, and for the rock alone, without the clay seam, we have this rather stiff and strong behaviour here. And in fact, it turns out this strength is about 60 megapascals, which I can't convert into tonnes per square foot for you, but it's pretty strong, okay? It's basically the strength of concrete. However, with the clay seam, what you see here is that the capacity of the pile tip is substantially reduced, and also its stiffness is substantially reduced. So that clay seam does indeed affect the overall behaviour of the pile tip. And we can look at this in a parametric sense by defining a couple of correction factors. I find it's always useful to look at these sorts of effects in terms of a correction to the ideal situation. So we define here a base capacity correction factor, BCR, which is the base capacity with the clay seam to the capacity without the clay seam. And similarly, we can define a stiffness reduction factor for the base, BSR, as the base stiffness, load divided by settlement, with the seam to the base stiffness without the seam. And so here's some parametric studies of that situation. Here is our base stiffness reduction factor, BSR, and here is the other one, the base capacity reduction, BCR. Let's just look at this top one now. This is the base reduction stiffness factor. This is the relative thickness of the clay seam divided by the diameter of the pile tip, and this is the relative distance of the clay seam from the bottom of the pile, going from 0.8 diameters down to 0 diameters, which means that clay seam is right at the bottom of the pile tip. And what you see is more or less what you would expect, that the thicker the clay seam, the greater is the reduction in stiffness. And also, the closer the clay seam is to your pile tip, then the greater is the reduction. And we have a very similar situation here for the capacity. So you see, that clay seam has a very dramatic effect potentially on both capacity and stiffness. Now, it's interesting to compare those theoretical studies with some design recommendations. And we have some that we use actually in the city of Sydney, where I live, that have been developed on the basis of empirical observations from a whole number of load tests by Pells and his co-workers. So this is now capacity reduction factor versus relative thickness of the clay seam. And we talk in terms of various classes of sandstone and shale. This is sandstone here. Class 1 sandstone is really good stuff. Class 2, you've got a few flaws, and by the time you get to Class 5, it's just riddled with clay seams and imperfections. And these ranges here, the steps here, are the design ranges that are suggested by Pells and his co-workers. This is the theoretical line transposed from the previous diagram for a depth of clay seam of 0.2 diameters. This is 0.8 diameters. So what you see is, in fact, that there is a general correspondence between what we calculate and what we use in design practice on the basis of empiricism, although these design values are fairly extreme and are really most relevant to where you have the clay seam fairly close to the tip of the pile. If the clay seam is much further down, then the reduction in capacity is rather less than these design rules would indicate. So let's then look at the overall pile, because what we're focused on up to date is the pile tip. Now, of course, we have another component, the shaft, which provides capacity and stiffness. So how does the overall pile react to that clay seam? Well, when we incorporate the reduction in capacity and stiffness of the pile tip into this analysis, what we find is illustrated in these two diagrams. And again, this one here is really a pile capacity reduction factor for the overall pile. It's the pile capacity with the clay seam to the pile capacity with no clay seam, going from 0 up to 1. And here we plot the pile length divided by diameter. And we've got a particular thickness of clay seam that we're examining, and we've got different depths of that clay seam. And what we find, if I can just summarise, is that as the pile gets longer, as the length to diameter increases, the reduction in capacity compared to the case of no seam increases. So we don't have such a dramatic effect of the clay seam on the overall pile when you have the shaft contributing. And of course, if that clay seam is relatively deep, then its influence is even less. So I guess the good news is that when you have clay seams and you have a fair amount of shaft friction and stiffness, the overall effect isn't quite as dramatic as the one that we saw in the previous slides. And this is a similar diagram which shows the effect of the clay seam on the stiffness or settlement characteristics of the pile. So just summarising then, the greater the amount of load that we have carried by the shaft, obviously the less is the effect of the clay seam on pile capacity and settlement. And so the stiffer the soil is along the pile shaft, or the more slender a pile, the less important is the clay seam. However, I think you'll see that over-idealisation, ignoring the presence of clay seams, can certainly lead to some negative consequences as far as your prediction of pile capacity and settlement is concerned. If I can just summarise very briefly the effects of a clay seam on a group of piles, it turns out, can be affected by a clay seam rather more than a single pile for two reasons. One is that the clay seam, relative to the overall dimensions of the pile group, will be closer than it is for a single pile. So it will sort of enhance the ability of the overall group to behave differently. And the other thing is that we find that with a pile group, you tend to have more load coming down onto the base of the piles than you do with a single pile. And again, that means that the base is going to be more influenced than the shaft. So clay seams are nasty, potentially, and we need to try and incorporate them where we can into our design. The next problem I want to look at rather briefly is what happens if piles are founded in a layer of variable thickness. And there are two or three consequences that we need to understand. The first of these is that if the piles are of different length, then they're likely to be of different stiffness. And so once you put vertical load on a pile group which does not have a uniform stiffness, then even though the load is vertical, the overall group will tend to rotate. It will tend to rotate towards the less stiff side of the group. And so what that means is that you may actually have a lateral response generated by a vertical loading. A second and rather interesting characteristic, and I didn't really realise this until I had a job in Hong Kong a couple of years ago, which I'll show you very briefly, is that when you have layers of non-uniform thickness and you carry out a reclamation, then you will get not only vertical movements, but you'll also get lateral movements as well, particularly near the edge of the reclamation. And such movements can interact with the piles and influence their behaviour. And so I don't have time to go into this one in detail, but let me just give you the bare bones outline of this case. This was a building, a 27-storey residential building that was supported on 144 steel H-piles on a reclaimed area. And they were driven to a harder stratum, not to rock, but to a harder stratum. Now, this reclamation, there was some soft soil on the site, and so there were large settlements adjacent to the building, and that was expected. And so what we found was that there were differential settlements of about a foot between the pile-supported building and the driveway that was obviously not pile-supported. So that was expected. What wasn't expected was that there were also lateral movements near the building because of the fact that the thickness of the clay, the compressible clay, was non-uniform, and also this building was getting towards the edge of the reclamation near a river close by. And what in fact happened, we have convinced ourselves, is that these lateral movements actually generated very large bending moments and shears in the piles, and cracks developed in the pile caps, and some piles were actually detached from the pile caps, so they rotated so much, and of course they settled, that they actually came out of the cap. And so this caused a rather nasty cracking of the building. Now, this just shows you some of, in one location, some of the differential settlements, not as great as in other places. This shows you one of the exposed pile caps, a fairly substantial pile cap with a really ugly crack going through it. Unfortunately, I don't have in this one pictures of the detached piles, but there were, in addition to these crack caps, piles that were actually detached. So there had to be quite a deal of remedial work done to those pile caps and a restoration of the piles to ensure the continued functioning of that building. The next case I'm going to describe, and it's a very quick description, is what happens, or what can happen, when you've got an underlying compressible layer. And this is a very nice case that was published many years ago now by Golder and Osler in the Canadian Geotechnical Journal. But one of the beauties of case histories is that you can come back to these and always learn. And this is the soil profile here. We had here a group of piles for a series of furnace foundations, and they decided that they would found the piles in this compact sand here. Now, unfortunately, lower down here, below the tip of the piles, there was one of the classic formations in Canada, the leader clay, which is a very quick and compressible clay once it goes beyond its pre-compression limit. What these people had done, not Golder because they told the story afterwards, but the designers had come in and done a pile load test, founded a single pile here, and what they found was, under the working load, it settled a millimetre. Only a millimetre. Terrific. Only a millimetre. Let's allow for group effects, so we expect settlements of 3 to 6 millimetres. Great. Well, what they actually measured after several years after was a maximum settlement of the order of about 74 or 75 millimetres and counting. And of course, what happened, if we go back to the previous diagram, was this, that whereas a single pile driven down here will have very little influence on this compressible clay layer here, a group of piles, which of course is of much greater extent and whose pressure bulb is much more extensive, will indeed load up the leader clay. And that's what happened. And then the post-mortem here, Golder and Osler indicated that they reckoned that there could be about 65 millimetres of settlement coming from the leader clay below. So this is a warning sign. It's very common, I've found, for clients to want to found their piles up as high as they can, obviously to save money, and there may be compressible layers below. And I think you need to think very carefully about how you do the assessment of settlement in particular and capacity as to whether or not that's a sound strategy to pursue. So the lessons from this, and there's always lessons to be learned: don't use single pile load test data to predict group settlements without proper ground characterisation. By all means use pile load tests, I love them, but be aware that the group has a different volume of influence than a single pile. And of course compressible underlying layers can cause substantial increases in settlement. The last geological imperfection I want to talk about is the effect of a boulder. And just to show you how boulders can occur, this is a slide that was provided to me by Dr. Manfred Nussbaumer from the Züblen company in Germany. And he'd done a project in Germany where they drilled a couple of boreholes reasonably close by and found dense sand, medium dense sand here, a bit of clay, marl, but that looked fine. And then when they were actually excavating for construction, what did they find but this rather ugly boulder here? And so boulders can arise in these sorts of situations, particularly, I guess, if they're in glacial regions, and they can influence the behaviour fairly significantly. And my interest in this, of course, Australia is not a glacial region, not to my knowledge, but I was involved in a project where there were, in fact, boulders in the subsoil left over from an old canal revetment. And the piling contractor had used jack piles and had installed the piles by jacking and come to the conclusion that these piles were good for over 4 meganewtons or 400 tonnes. And they're relatively short piles, about 6 metres long. This is an idealisation of the piles. Now, what happened in fact was that when they did a load test, they only got a capacity of about 250 tonnes, substantially less than the 400-tonne jacking force that had been required to install the pile. And so the question was, what in the devil happened? Well, the hypothesis that we examined was that these piles, or some of these piles, of course it didn't happen to every pile, only to a few, some of these piles had actually rested on one of these boulders that was part of the revetment. And so when we modelled that, what we have here is load versus settlement. We had a load settlement curve on initial loading or jacking in of the pile that looked like this, and indeed you get up to about 400 plus tonnes. Now when you unload, you come down here, but the reason that you've got the high capacity is that you've got the boulder actually becoming part of the pile while the installation is going on. So you get a big end bearing capacity. Now when you unload, you finish up getting the shaft detaching from the boulder because the boulder stays down and the shaft comes up. And so you finish up with a gap between the toe and the boulder. So when you reload, everything looks fine while the shaft is still reloading. But once you mobilise the full shaft capacity, then basically you're going through what is effectively a gap until you recontact the boulder, in this case about 100 millimetres later on. And so the effective capacity of this pile is significantly less than what was originally thought because of the fact that the boulder gave you this artificially high capacity in the first place. So the main features then in situations where piles may be founded on a boulder are that you get an increased resistance during installation. The shaft then detaches from the boulder when you release the load, and you get a smaller apparent resistance and stiffness of the pile on reloading until the shaft recontacts the boulder. But in fact, that may be at a settlement which is unacceptable. And so obviously the effects are more pronounced on relatively short piles where most of the resistance is from end bearing, and that in fact was the case with this particular project in Australia. I want to now say something about the idealisation of piles because I want to go on and talk about the possible consequences of construction imperfections. Here is our design idealization. Almost invariably, we, as optimistic geotechnical designers, assume a perfect cylinder. Regrettably, what we occasionally get is this. You've got debris at the base, so you've got the so-called soft toe because the drill shaft has not been adequately cleaned. You've possibly had too rapid an extraction of the casing, so you get necking, and you've got voids or weak areas because of inadequate trimming. So you finish up with a structural element which is rather different from the idealization that you made during the design. Now, in order to look at this particular problem and try and gauge the consequences, what we can do is that we can idealize the defects as elements of different diameter, stiffness and strength. And then we can carry out a pile-soil interaction analysis to look at the two main effects, which are a reduction in stiffness and a reduction in capacity of the pile. So let's look at a somewhat hypothetical case here. Here is load as a relative to the ultimate geotechnical capacity, 0 to 1. Here is pile head settlement. Here is the idealised case with a rather disturbingly large defect here. 8 metres long, 8 metres below the top, just for the sake of argument. Here is our ideal load settlement curve, this full line here. This is for a perfect elastic pile. Now, if we have a pile that has a strength, compressive strength, concrete, in excess of 100 megapascals, and good luck if you can construct that, then you have this sort of relationship. And the only way that you would recognise that there was a defect is that it settles just a little bit more than the perfect pile. However, if we start getting to realistic concrete strengths of 50 or 35 megapascals, then what you see is that basically the pile is sort of behaving reasonably well, and then all of a sudden, bang, it fails. And so the strength of that pile is then governed by the structural strength of the defect rather than the strength of the supporting ground. And if you think that may be a little bit idealised, well, in fact, here's a case that was published by Briaud a few years ago, some piles in Egypt which had displayed unexpected behaviour and had been exhumed. And indeed, this is load versus settlement, and they got a very handsome looking load settlement curve until they got up to about 1,200 kilonewtons, 120 tonnes, and then bang, it failed. And indeed, what did they find when they exhumed that? There was a big structural defect that had caused that abrupt failure. Now, if we're interested in looking at this a little more generally, we can define what I've called here a structural integrity factor, which is the ratio of the stiffness of the defect, modulus times area divided by length of the defect, divided by the stiffness of the intact pile. And so that integrity factor, at best, is infinity. If you've got infinite integrity, in other words, 0 length of defect, then that's a perfect pile. If you've got very small numbers here, it means you've got a very small modulus or a very large length of this defect. And we can also then, if we're interested in what effect this structural defect has on the stiffness of the load settlement curve, then we can define a stiffness reduction factor, the stiffness of the defective pile divided by the stiffness of the intact pile. Now, here's a diagram that summarises two things. One is a series of theoretical calculations, and the other one is some experimental data. Now, on the vertical axis, we plot the head stiffness reduction factor, RKS. In other words, the stiffness of the defective pile divided by the stiffness of the intact pile. And here we have the structural integrity factor ranging from 0.01, which is disgusting, through to about 10, which is good. This band of results are a range of numerical solutions depending on where those defects are located. But they are are relevant to defects that range from right at the top of the pile, where you get the most dramatic effect, to about 0.4 lengths below the pile. So there's this range depending on where the defect is located. Now these dots represent experimental data from a series of carefully controlled laboratory tests carried out by one of my former students, Dr. Kenneth Zhu. And you'll see that basically those points follow the theoretical predictions reasonably well. So indeed, structural defects influence the stiffness of the pile quite dramatically. I mean, a really bad defect can reduce the stiffness by a factor of 3 or so compared to your intact pile. The settlement is, in other words, 3 times more than you would have anticipated. Now, I'm not going to go into detail on the effects of defects on groups, but just to summarise what would happen, and this is a not uncommon situation. You have a group of piles, and maybe integrity testing has indicated one or more of these piles has flaws in it. What happens to the group? Well, firstly, you would expect additional settlements because the stiffness of one or more of those piles is less than it should be. There will also be an increased non-uniformity of axial loads because, obviously from structural principles, the less stiff a pile is, the less load it attracts. You will get lateral deflections because now, even under vertical loading, you don't have uniform support, so you'll get lateral deflections, you'll get a cap rotation, you may get additional moments in the pile, and particularly at the pile cap connection, where generally your moments are largest, and so you may finish up with concerns about the structural integrity not only of your defective piles, but also of the connections with the pile cap. And you get these sorts of things as well with piles of varying length. Now, let's look at what happens if you have their structural defects. These are a bad pile. But what happens if you've got a soft toe? Well, basically you get a reduction in stiffness of the base of the pile, which in turn causes a reduction in the stiffness of the pile head, and that tends to be, of course, more severe after the shaft friction is mobilised. And that leads to an apparent reduction in the pile capacity. Although the ultimate capacity, if we're really interested in ultimate capacity, you may still have the ultimate capacity available, but it may occur after very large settlements, because if you've got a blob of soft clay, for example, at the bottom of the pile, as you keep loading, the clay has nowhere to go, so sooner or later it'll stop compressing. But that may be after you've gone a long distance. There were some very interesting tests that were carried out in Taiwan a few years ago by Wu and Mo, where they had firstly piles with a clean base and then piles where they introduced a soft toe deliberately. And obviously you get quite a different behaviour. With the clean base, in this particular case, you got this sort of load settlement behaviour. When they introduced 25 centimetres, basically 1 foot of thick slime at the bottom, then obviously they got a smaller apparent capacity and certainly less stiff. Now, if we're looking at what the consequences are then on a particular pile, because this is again is related to what happens at the pile tip primarily, we can in this case treat the soft toe as in fact a compressible element of the pile for the purposes of our analysis. And that reproduces, we found, the main features of the greatly increased settlement once the shaft resistance is mobilised. We in fact tried some large strain finite element analyses and got rather similar results with that more complex analysis. And here's just an example of the comparison that we can get between what we calculate and what is actually measured. Now these are different piles now. These are piles C and D. Pile C is a good one where the base was properly cleaned and you get this rather nice load settlement behaviour which we can simulate reasonably well. Pile D, which has 1.5 metres, 5 feet of debris at the base. It's rather interesting. This pile showed really good behaviour up until a load of about 9 or 10 meganewtons, and then it took off. So clearly that represented the shaft doing its thing, and then once the shaft friction had been mobilised, then of course the base compressed substantially. But this was a 32-metre long pile, so clearly the shaft friction was doing a job here. And in fact, we were able to simulate that reasonably well with this fairly simple sort of approach. Now I want to go on with that soft toe story and tell you about an interesting case in Hong Kong that was settled in court a couple of years ago. This involved two high-rise building blocks that had exhibited uneven settlement. I'm not sure how many of you know this, but in the late 1990s, there was the existence of unconventional piling practices, shall we say, where some piles had been found to be shorter than they were supposed to be. And as a consequence of that, measurements of settlement of buildings started to be taken fairly routinely. And these two particular blocks were monitored for settlement, but only after they'd reached about level 17 of a Plan 41. What happened, of course, was that the settlement monitoring indicated that these buildings were not settling uniformly, but they were in fact tilting, and they were settling a lot more than had been anticipated. What they then did was that they called a halt to construction at floor 34. They drilled through each of these drill shafts, and these were 2.3 metres, I think, in diameter, each one of these, supposedly with a bell. And what that pile coring showed was that a number of the piles were short or were not properly founded. All the piles were supposed to go through to grade 3 or better rock in Hong Kong. A lot of them did not. And so what happened was then there was a significant period of evaluation where a whole series of analyses were carried out to assess the risk of proceeding with construction and of underpinning the buildings. Because clearly the contractor wanted to continue with the construction and to finish it and do some underpinning and thereby correct the uneven settlement. These are the blocks. This comes from the front page of a Hong Kong newspaper. The only time we get onto the front page as civil engineers is if some catastrophe occurs. Now, this is such a case. These were two blocks labelled D and E. They were at level 34 or 41. This is a 6-storey secondary school adjacent to these blocks that were being built, and these blocks were tilting towards that school. And here's different perspectives here, and of course an emotive picture showing young schoolgirls sort of in dire peril of being crushed by these tilting buildings. These are the conditions here. There was fill, there was a thin layer of marine deposit, alluvium, and then extremely weathered granite. Here, class 5, and then the slightly weathered rock, which was supposed to be the founding stratum for these large diameter bored piles. This is a plan of the two buildings showing each of the large diameter bored piles, 18 piles in each, 2.3 metre diameter, belled to 3.4 metre diameter. These are the time settlement measurements. Settlement here, time here, and you'll see that this is for Block E. The low side didn't settle very much. The high side had settled, this is from floor 17 to floor 34, about 40 millimetres, where the overall settlement under 41 was supposed to be about 15 to 20 millimetres. So clearly something was not right. Now, interestingly, when they did this investigative coring, what they actually found was that they induced additional settlements of the building of up to 30 millimetres. So this in itself is an interesting lesson, that when you do investigations below a building of this nature, inevitably the disturbance you cause to the ground is going to have some impact on the existing foundations, and indeed it did. Now this is, again, from the newspaper. This is the structural engineer's representation of the pile conditions. These grey things here are the piles. This is the bedrock, which was supposed to be the founding stratum. The blue bits are assessed to be drilling fluid or something really soft and squishy. The yellow bits are assessed to be highly decomposed granite, not founding material. So you see a lot of yellow, up to 20 metres of yellow above the rock. In other words, the piles were 20 metres, up to 20 metres shorter than they should have been. And this is a diagram which shows you the assessed condition of the piles. Green is where the piles were found to be in accordance with the piling records. That's more or less the same length as the piling records indicated. Pink is where the piles were found to be up to 10 metres shorter than they should have been. The red are up to between 10 and 20 metres short of where they should have been. That was block D. This is block E. Lots of red and pink. And foolishly, all sort of located on one side of the building. Now, clearly, these people didn't recognise that if you're going to do this, you should sprinkle them around uniformly. What we did in our assessment, and we were working for the Hong Kong Housing Authority, we used this program called PIGS, Pile Group Settlement, which we developed and in fact kept developing during the course of this. This program takes account of different pile types within the group. It accounts for soft toes and variable pile lengths, and we in fact used a different model for each pile in the group because this was the reality. There was no point in trying to use an idealised program where all the piles are the same. This was not such a case. This program also allowed for settlement and rotation under vertical loads, although it assumed that the piles were pinned to the cap. And we also incorporated the facility for having ground movements due to drilling imposed as external soil movements. We calibrated the analysis against the measured settlements. So what we have here for 3 sections across and down the building is the settlement versus the location, and these dots represent measured settlements and the dashes represent the calculation. So we did a little bit of adjustment, but we calibrated our model and it fitted both buildings pretty well with a consistent set of parameters. What we were able to do then was that we were able to simulate a whole series of forward scenarios. What would happen if they proceeded with construction without any action? What would happen if they proceeded with construction after underpinning and so on? Well, what we concluded from this analysis was that firstly, the uneven settlement of the buildings could be explained by the presence of piles with soft toes, and you see extreme soft toes, inferior founding conditions and shorter shafts than designed. And there was, of course, also concern about drilling-induced ground movements during the investigations because the contractor's remedial scheme involved drilling 68 2-foot diameter holes into which they would grout steel H-piles. Now, if you drill 68 2-foot diameter holes, you're removing a lot of soil from a very highly stressed region, and that's going to impact on the existing foundation. So we were really concerned about that similar movements could occur during remedial pile installation. We looked at various alternatives, installing additional piles, but we were really concerned about the risks involved in installation, partial demolition to use existing piles. And one of the brilliant schemes that somebody came up with was, why don't we leave the piles as they are and then demolish 21 stories, so we have a 13-storey building. Well, nobody wants to live in a 13-storey building. 13's unlucky for a start, and you're surrounded by 41-storey buildings. And complete demolition. And in fact, the last alternative was adopted, and those 2 buildings were demolished over the following couple of years. There's still nothing built on there because it's all bad feng shui, and nobody wants bad feng shui in Hong Kong. Just as an addendum, the main contractor got hit for a judgment of 250 million Hong Kong dollars, still a lot of The piling subcontractor is serving a 10-year jail sentence at the moment. Well, what happens if we find that we have imperfections? How do we cope with the consequences of imperfections? Well, there are three issues here. The first is investigation. And clearly, as this case has shown, we need to take extreme care to avoid further disturbance and settlement when we're actually doing investigations to try and find out what's there. Any SPT testing that you do must be done very carefully. You must be very specific about the processes. You mustn't sort of extract too rapidly, otherwise you cause suctions and that loosens sand and so on. And you need to be very fastidious about balancing fluid pressures in drill holes or cores. In terms of design issues, you may need to correct uneven settlements, because if you've got a building, as we had here, that was already tilted, you need to do something to try and correct it before you finish the building. And that means that you have to design remedial and enhancement works as well, and of course you have to look at the load sharing between old and new elements of the foundation system. Now, just very quickly, the correction of uneven settlements. There are a whole series of methods that can be used. And these are in two categories, which I classify firstly as hard methods. These are methods that structural engineers like because you actually do things to the foundations and the buildings, like anchor stressing. You actually pull the building down on the high side. Additional loading of the high side to make it settle more. Cutting of piles to make it settle more. Jetting of soil below the pile tips to make the high side settle more. Jacking of the foundation on the low side to try and jack the low side up. Or fracture grouting. All of these are basically intrusive, invasive methods, hard methods. We, in fact, on another project, not these same two buildings, we in fact used a combination of a couple of those hard methods. We actually cut a series of piles below two buildings. In one building we cut 51 piles, the other one we cut about 20. And that's of about 300 piles in all. And we also did anchor jacking, and we also did soil extraction, which I'll talk to you in a moment about. So these hard methods can be used in combination with other methods. The soft methods, these are methods where you get nature to do your dirty work. And the first of these, soil extraction, where you actually withdraw soil from the ground very carefully. Dewatering, where you try and induce settlement by reducing pore pressures and so increasing effective stress. But that's a bit dangerous because, again, dewatering is not the most precisely controlled process. Compensation grouting, where you try and jack up the low side by pumping grout into the soil. And another method that I'll show you very briefly that we developed and we thought we were going to use, but we didn't in the end, removal of soil support, or RSS. Soil extraction has been most famous in correcting the tilt of the Leaning Tower of Pisa. And it was done in Pisa by a series of sub-horizontal drill holes where soil was extracted from under the Pisa Tower. The soil basically closed up, and that gave a half-degree correction on the tower, which will give it another 300 years of life at least. But that's not the first case. There have been cases in Iran, for example, where under this leaning grain elevator there was a series of chain cuts made on the high side of the building. They dug a trench and they put in a horizontal chain, extracted soil, and managed to correct that tilt quite successfully. This RSS method that we had proposed to the Housing Authority to use, and we almost got them to agree to it, and then they backed out, cold feet. The idea here is that you drill a whole series of boreholes outside the high side of the building footprint, so you don't go inside, you go outside, and what that will tend to do is to cause the high side to settle, and that will take the piles hopefully down with it. Now, to test out the general idea of this, one of my colleagues in Hong Kong, Dr. Charles Ung, did a centrifuge test, not on piles, but this is just on a shallow foundation, where he introduced a foundation that was deliberately tilted in the first place. and then with his clever little robotic tool, he came in there and did a whole series of excavations. Here's the footprint here. Here are the holes that were drilled in sequence, every second hole, and then they came back and corrected it. Here's the tilt of the building. It started off at 1 in 27, very extreme, and as the soil was extracted, then the tilting was corrected until we finished up with 9 bore holes at 3 metres outside the prototype size, where we went down to 1 in 67. So that general process actually will work, and it's actually been used in China, I believe, to correct shallow foundations, although I don't know whether anybody's used it for piles. Just very quickly, because time is getting on, foundation enhancement works. If we're looking at defective piles, we can look at the possibility of repairing existing piles to enhance their capacity and stiffness, although that's not always easy to do. We can look to extend the pile caps, make use of the pile caps to give us additional strength and stiffness. This is something that people tend to be hesitant to do, but we've done it on the odd occasion and it seems to have worked out. And of course, there's always the possibility of adding new piles or underpinning to strengthen or stiffen the existing foundation. And when you do that sort of underpinning process, we have sometimes a problem in terms of controlling the way that the loads are distributed between the existing piles and the new piles. The new piles may well be stiffer than the existing piles, so there may be a load concentration on them. How can we avoid that? Because in some cases, for example in Hong Kong, the design of piles is based on the most heavily loaded pile. You have to have a factor of safety of 2 against the most heavily loaded pile, and that kills many remedial schemes. Well, what we can actually do is to use what I've called control stiffness inserts on the pile head. And the whole idea is that here's the pile cap, here's the pile, and we introduce a lump of compressible material, neoprene or whatever, and what that does is it actually gives you another compressible element on top of the pile, and so reduces the stiffness of that pile effectively. And they have actually been used. I persuaded somebody to use them in Hong Kong, and here they are in place waiting for the pile cap to be poured. So you can tune the stiffness of these inserts to give you the required load distribution, and you can work out what your target stiffness for those piles is. So what we've found is that additional piles can restore the performance of a defective pile. I had an example to show you, but time does not allow that. In general, the non-uniformity of load distribution that we get in such a system can be relieved by use of these inserts, and that is an advantage where the design is controlled by the maximum loads that you calculate in the piles. So let me just make a few concluding remarks. In terms of imperfections, they may create unforeseen problems for pile designers. And of course, the significance of those imperfections depends on their nature and extent. I think we should develop a mild form of atelophobia, fear of imperfections, coming from the Greek, of course, atelos meaning unfinished or imperfect, and phobia meaning fear. Fear of imperfections. We should always be on the lookout for that possibility. The more important natural imperfections may include clay seams, compressible layers below the founding levels, and compressible soils of uneven thickness, and of course differences in founding conditions. Now, where you have, for whatever reason, variable founding conditions, then you have the potential for, even under vertical loads, differential settlements, lateral movements, head rotations, and additional bending moments in the pile heads under axial loading. In terms of construction-related imperfections, structural imperfections can be nasty. They may not show themselves up until the pile fails, and failure can be quite sudden. And there may be some reduction in head stiffness as well. Geotechnical imperfections, such as a soft toe, will lead to a reduction in stiffness of the pile, which of course depends on the length to diameter ratio and depends on how much shaft friction you have available. Coping with imperfections, you need to be careful in investigation. Don't make the problem worse. I've not only this problem in Hong Kong, but there's another problem I've been involved with in Singapore where the actual investigations have exacerbated the problem you're trying to solve. And there are these hard and soft methods available if you're really bold and desperate to correct uneven settlements. When you design foundation enhancement works, it really is an interesting and challenging problem because you don't start off with the ideal situation where you've got all the pile group there. You normally have a pile group that A is imperfect, B has already been loaded in some rather complex way. Now you're introducing new elements and you're introducing generally additional loading. So it's a fairly complex problem, and you can control to a certain extent how that pile group behaves by the use of these inserts. Finally, this is the front page of the classic theoretical soil mechanics book by Terzaghi, 1943. It's the book that basically persuaded me to do soil mechanics for my graduate studies. I didn't really understand very much in this book when I looked through it and tried to study it as an undergraduate, but there was an element of excitement and uncertainty about it, and that's really what drove me to do this. And the uncertainty, I think, is reflected in this statement by Terzaghi. If the engineer is fully aware of the uncertainties involved in the fundamental assumptions of his computations, he's able to anticipate the nature and the importance of the differences which may exist between reality and his original concept of the situation. So, ladies and gentlemen, I hope that this talk has given you some idea of what sort of effects some of those differences may have on pile behaviour. Thank you very much.
Do you have any questions for Professor Poulos? Don't be shy.
Too timid, that's okay.
Raymond.
How can we make this size of the work
Yeah, this, what we did there, there's no established design method for this. We went through a very comprehensive series of three-dimensional finite element analyses to try and it was really trial and error, because one of the interesting things you find is that such a common problem as drilling a borehole into the ground does not have too many theoretical solutions that we could find in the literature, particularly if you've got a situation where you have loading on the ground surface, and even more particularly where you have uneven loading because you've got the building here and you've got nothing outside and you've got a hole. So in fact, you have a non-axisymmetric problem. It's a really interesting one. Nice PhD if any of you want to take it up, and probably only take you 5 or 6 years to complete.
Any other questions? I had a comment on the clay seam issue. I was involved, I was doing some pressure meter tests for, it was like 12, 13 years ago for the Hilton Hotel in St. Louis Airport. And I was drilling, the drill holes were made through the rock, and I was testing laterally with the pressure meter, but there were some clay seams, and so I was giving these high moduli values, and I was worried about the impact of the clay seams on the settlement. So I looked at the cores and warned the client about this. And then I remember talking to Ralph Peck about this and asking him how he felt. And he said, I've rarely seen a clay seam that is totally continuous.
Yes.
In other words, the rock will come back together from time to time. These clay seams tend to be pockets. Do you have any observations on this?
Yeah, well, obviously, how can I disagree with Ralph Peck? But he, yes, he's probably right that clay seams are not, no, I mean, this is idealized, but generally they're not uniform in thickness. and they do tend to occur in pockets, I guess, because of the geological origin. And if that's the situation, then clearly the assumption of a continuous clay seam is an upper bound to the effect, because when you restrict the amount of soft material, then you can't generate these alternate mechanisms of failure which give rise to the sort of reductions in stiffness and capacity I've shown here.
No other questions? Then it's my pleasure to give you this plaque in appreciation. It says, Certificate of Appreciation to thank Dr. Harry Poulos for delivering the 2004 Terzaghi Lecture entitled Pile Behavior, Consequences of Geological and Construction Imperfection at the occasion of the 13th Buchanan Lecture, Texas A&M University, Zachry Department of Civil Engineering. Thank you very much.
Thank you very much.
Now it's my pleasure to introduce the 2005 Buchanan Lecturer, Professor Thomas D. O'Rourke. Dr. O'Rourke is the Thomas R. Briggs Professor of Engineering at Cornell University. Professor O'Rourke is a member of the U.S. National Academy of Engineering and an elected Fellow of the American Association for the Advancement of Science. He has received several awards from professional societies, including the Collingwood, Huber Prize, C. Martin Duke Lifeline Earthquake Engineering, Stephen D. Bechtel Pipeline Engineering, and Ralph B. Peck Awards from the American Society of Civil Engineers. He has won the Hogan-Tugler Award from the American Society for Testing and Materials, the Trevithick Prize for the British Institution of Civil Engineers, the Japan Gas Award, the Earthquake Engineering Research Institute Award for Outstanding Paper, and a Distinguished Service Award from the University of Illinois College of Engineering. Wow. In my book, that amounts to an A+ for awards. He served as president of the Earthquake Engineering Research Institute and a member of the U.S. National Science Foundation Engineering Advisory Committee. He's a member of the executive committees of the Multidisciplinary Center for Earthquake Engineering Research and the Consortium of Universities for Research in Earthquake Engineering Board of Directors. He has served as chair of the executive committee of the ASCE Technical Council on Lifeline Earthquake Engineering and the ASCE Earth Retaining Structures Committee. I'm afraid, again, this amounts to an A+ for service. He has authored and co-authored over 290 technical publications. He has served on numerous earthquake reconnaissance missions and has testified before the U.S. Congress in 1999 on engineering implication of the 1999 Turkey and Taiwan earthquake, and in 2003 on the reauthorization of the National Earthquake Hazard Reduction Program. He has served as chair or member of the consulting boards of many large underground construction projects, as well as a peer reviewer for projects associated with highway, rapid transit, water supply, and energy distribution system. He's investigated and contributed to the mitigation of the effect of extreme events, including natural hazards and human threats on critical civil infrastructure systems. His research interests cover geotechnical engineering, earthquake engineering, engineering for large geographically distributed systems, underground construction technologies, and geographic information technologies and data management. I might add that I also know Tom as a very kind and positive person. You cannot help but feel good when you talk to him. The title of the 13th Buchanan Lecture is Soil Structure Interaction Under Extreme Loading Conditions. Please welcome an outstanding engineer and a good friend, Professor Thomas O'Rourke.
Thank you very much, Jean-Louis. And also, I must say I'm very excited to be here. There are many instances when I've come to Texas, but I never got by College Station, so I'm really, at this visit, doing something that I've really wanted to do for a long time. And I must say that in meeting the faculty and in meeting the students here today, it's been just a great pleasure to interact with people, and I'm extraordinarily pleased to be here. In giving this talk, I also should start by recognizing some coworkers and colleagues who have contributed to this work. They include Jim Turner, Harry Stewart, Sang-Soo John, Yu Wang, and Peijing Shi, and a number of other people that I don't have the time to recognize, but clearly talking about a body of work is something that involves the collaboration of many people, and I owe them a debt of gratitude for the great contributions that they've made to what I'm going to be talking about, which is really a joint effort. The talk today is called Soil Structure Interaction Under Extreme Loading Conditions, and if, I'll go back for a second, we look at the diagram here, or the pictures in the very first slide, you will see a condition or an instance of extreme loading. This happens to be Balboa Boulevard. It's in the northern San Fernando Valley, and during the 1994 Northridge earthquake, this particular area was subjected to liquefaction, which caused a lateral displacement of about 2 to 3 feet directly south, and it ruptured 2 very large diameter water pipelines. One was 5-foot diameter, the other one was 7-foot diameter. That cut off about 20% of the water that was taken from the Los Angeles reservoir, thereby depriving many people of water after the earthquake, which after an extreme event like this is really important for fire protection. And it also ruptured a gas pipeline. You can see gas burning here, but this is just a distribution line. I'm going to concentrate on this picture a little bit more closely. There was actually another gas pipeline here, a trunk line which ruptured, and that sent a fireball in the air about 300 feet high and burned down the surrounding structures here. So these structures were literally flooded from the bottom and burned from the top, and it's all related to soil structure interaction of some very important critical facilities. I may also add that there were a number of other oil and gas pipelines at this location which survived the deformation. So it's also a very interesting case history, which I'm not going to treat today, but I'm going to stimulate your interest in it in terms of the relative capacity of different underground structures to sustain themselves under extreme loading conditions. So with that, I'm going to blank the screen a little bit, and I'm going to try to define extreme loading. For the soil, it involves large, plastic, irrecoverable deformation, and that deformation is often associated with geometric changes in the soil mass. And I think this is where some of the modeling challenges are coming in, because as deformation progresses in soil masses, there can be distinct disruptions in the geometry of that mass, so that we're not only talking about material nonlinearities, but we're talking about, and sometimes some very extreme, geometric nonlinearities. These interactions of soil under these conditions will create peak loads on embedded structures, and the ability of those embedded structures to survive these kinds of deformation becomes an important part of our design considerations with respect to disasters. So extreme loading can be looked at as being caused by a number of natural and perhaps some unnatural disasters. Earthquakes and floods, landslides, subsurface collapse and surface impacts, explosions, subsidence caused by mining and withdrawal of underground fluids, deep excavations and tunneling. All of these have the potential to generate movement in the extreme of the ground against underground structures, and that interaction is something which is very important. I think we're all sensitive to the impact of disasters, particularly given the experience of the U.S. in the recent past. From the World Trade Center disaster to Hurricane Katrina, extreme conditions of loading are becoming a very important concern, not only for geotechnical engineers, but also for the entire civil engineering profession. The topics I'd like to talk about today include geotechnical earthquake loading, because we have been studying extreme loading conditions in earthquake engineering for some years, and I think that some of the lessons we learn here have generic implications for extreme loadings under other applications, be they natural disaster or be they human threat related. I'm going to talk about Lifeline's system response to earthquakes from the perspective of what we are involved with or concerned about with regard to soil structure interaction will ultimately have some implication with respect to an individual structure. Certainly, Professor Poulos has talked to us a lot about the implications of settlements associated with pile foundations. What I'm going to try to do is to talk to you about the implications of extreme loading for large geographically distributed systems, and in particular concentrate on the Los Angeles water supply, but also draw some analogies to other large distributed systems. We, in being involved and concerned about extreme loading, not only have to be interested in the extreme loading of the soil, but that extreme loading of the soil often brings the structure which is embedded in it into an extreme loading situation, so it too becomes subjected in the extreme to plastic irrecoverable deformations and geometric nonlinearities. And I think that's where one of the major challenges is right now, is appropriately modeling the coupled problem of these extreme event conditions, both for the structure and the surrounding soil. And therefore, we need large-scale tests to validate our thinking, to qualify our models, and to provide a platform for the next generation of model development until we have pushed the pioneering edge of that system or that generation of models, and we then perform targeted large-scale tests to push it even further. And then finally, I'm going to talk about soil structure interaction during ground failure. In effect, I'm going to start with the system and work down to the individual components. And I'm going to start with a system that's 1,200 square kilometers and eventually talk about the interaction between grains of sand, which would be on the order of millimeters. We live in a world that is a beneficiary of many important resources that are delivered to us underground. Lifeline systems are certainly one of those areas where the buried structures that convey electric power in urban centers, gas and liquid fuels, telecommunication, transportation, wastewater facilities, and water supply, these structures being buried within the ground or being constructed underground, their fate is intimately tied to the fate of the ground. And one of the characteristics of modern infrastructure is the congestion associated with our underground environments. This is a picture of New York City that was taken in 1917. It is the corner of Wall Street and William Street, which nowadays is the very heart of the financial universe. In the 88 years since this picture was taken, the situation has not improved. In fact, here is another picture that was taken just a few days ago of an area close to the one that you see here, about 3 blocks away or so. I think you can see that it doesn't take much imagination to understand that if there is a loss of ground here, which causes a collapse of a water main here, that the undermining then created by that water main can cascade into a telecommunication system or to electric power system, and that can then cascade further on to create serious system consequences. The ground, in many ways, is the glue that holds infrastructure together. It is both the perpetrator and the mediator of extreme loading, and understanding its interactions and the subsequent interactions that can be generated by the improper or difficult behavior of the soil becomes an important part of holding our entire infrastructure together. What I'd like to do then is to talk about some explicit examples of extreme loading. I'm going to concentrate on geotechnical earthquake loading. And under earthquakes, we will generate ground deformation. In fact, earthquakes have been known to generate some of the most dramatic forms of ground deformation in terms of fault movement, where buried structures or underground structures can be subjected to tension, compression, depending upon which way they cross the rupture, and also landslides and soil liquefaction in the form of lateral spread, which can generate almost fault-like effects at the margins between the moving ground and the relatively stable ground surrounding it. In fact, there have been a number of system-wide views on how to deal with permanent ground deformation, and here is a sort of generalized approach to the investigations that one might make for a large distributed system, starting with reconnaissance and project investigation and going all the way down this vertical line to site-specific subsurface investigations to try to deduce what the implications in earthquakes would be with respect to regional uplift and subsidence, surface faulting, landslides, liquefaction, which can cause flow failure, and settlement, buoyancy, and lateral spreads, and then consolidation of loose granular soils. There are also a number of dynamic interactions between the ground and buried structures that are caused during earthquakes, which involve some very interesting effects. Most recently, we recognize that when earthquakes occur, if you are within approximately 10 kilometers of the fault rupture, you get what we refer to as near surface or near source events. And these involve very large pulses at times of acceleration, velocity, and displacement, which can have some serious repercussions. Next, I'd like to talk about lifeline system response to earthquakes. And in doing so, I'd like to say a few words about geographical information systems. This is a tool that allows civil engineers, urban planners, and a variety of other people to, with software, manipulate, analyze, and display geographic data in digital form. But it's far more than just a map-based technology. Geographical information systems allows us to create a template of our physical infrastructure in the form of maps, and then to superimpose on those maps relationships in 3 and multiple dimensions that we never anticipated, perhaps, or never could see without looking at them in this common framework. And if we think of civil infrastructure systems, most of us concentrate on the physical environment. So we're either dealing with the built or the natural environment, for which there are so many data sets these days, and so many servers and so many different locations, that GIS allows you to draw data from a multitude of different sources and to put it on a common reference plane with your own data and understand its implications regionally and locally. But there's also the social environment, and some people would claim that civil infrastructure in its core is the social environment, and databases exist for us which are again geocoded, same geocoding which is used for the physical environment, where we can understand the demographics, economic patterns, and so forth of the populations that live in civil space populated by our infrastructure. So if we were to take a look, for example, at Landsat imagery for Los Angeles, there's a few things that we can see in this image which can be digitized and then collected. We have the San Andreas Fault up here. We have the Santa Monica Mountains over here. There's a Santa Monica Fault, which you can see very clearly delineated in this straight line feature. And then there's something else in this map which is quite distinctive that I don't know if people will recognize, that if I put this little circle here on the Malibu coast, that is the Malibu home of Arnold Schwarzenegger. Now, you might laugh, but in laughing, what you've done is acknowledge that every map has a personality, and it's really the human dimensions of maps that really tie things together. And by the way, Governor Schwarzenegger has indicated that he is very interested in building civil infrastructure to the tune of trying to find a bond issue for $50 billion in California alone. So he may well be our next civil infrastructure champion. In any case, this happens to be a map of Los Angeles showing all of the census blocks. These are locations that involve approximately 550 families that have common demographic, common economic characteristics to them. And if you want, there's 6,000 of these in the County of Los Angeles and about 2,500 in the blue part, which represents the city of Los Angeles. This literally is the finite element mesh for the social infrastructure of Los Angeles. So consider that geotechnical engineering through GIS can not only link and connect with the built environment, but it can link and connect with the social environment to integrate and understand the relationships among some very interesting different data and different characteristics of our infrastructure. The Los Angeles Department of Water and Power serves approximately 3.8 million people. The other provider in that area is Metropolitan Water District, which supplies water to smaller municipalities comprising the other 8 million or so folks in that particular area. It operates about 12,000 kilometers of distribution and trunk pipelines, where distribution pipeline is defined as 300 millimeters, or 600 millimeters or less in their terminology, and larger is the 600 millimeters. It covers an area of about 1,200 square kilometers. As part of work that we did after the Northridge earthquake, is we collected about 1,100 repairs in that system, which were sources of damage during the earthquake. We digitized the 11,000 kilometers of distribution pipeline and 1,000 kilometers of trunk pipelines because they were not in digital form at the time. And we integrated the 230 so strong ground motion records, which were of good quality from that area, into the GIS, along with a number of other features of the infrastructure. The manifestation of this is something in a map like this, which shows the San Fernando Valley here and the Los Angeles Basin over here. And all of these orange and then superimposed upon that blue lines represent the water trunk in blue and an orange water distribution system for Los Angeles. And what one can do in assembling this kind of information is they can get an inventory of the composition of the system. And one of the things that you'll notice if we look at the trunk line system, and this is characteristic of a lot of infrastructure in the United States, that about 78% or 76% of all the water distributed in Los Angeles goes through cast iron water mains. That's the exact same percentage, by the way, of New York City and a number of other major conurbations in the United States. And therefore, if one were to be looking for that component of the system that was most consistently distributed through the area, then one would focus on the cast iron system, because 76% of about 11,000 kilometers of pipeline represents on the order of about 8,000 of these linear extensometers, which are distributed across the sediments of the San Fernando Valley and the Los Angeles Basin. So we can make a fundamental observation, and that is the Los Angeles water pipeline network can be treated as a giant strain gauge. What we need to do is to take a pipe which is reasonably consistent in composition, like the 8,000 kilometers of cast iron, something that's reasonably sensitive to movement, and certainly cast iron is, because it is non-ductile, it's a brittle material, and then look at the repair pattern and try to systematically analyze that repair pattern to deduce something about how the ground was locally behaving en masse during that event. And so what one can do in GIS very rapidly is you can take the system of water supply in Los Angeles, you can put a grid on that. In this case, I'm going to demonstrate the effects of putting a 2 by 2 kilometer grid separation system. So each cell is 2 by 2 kilometers. Within that grid, then, we will count all of the repairs that occurred in that grid and divide it by the kilometers of cast iron pipeline that happen to be located in that particular cell to create a repair rate in terms of repairs per kilometer, and then to draw contour lines to indicate locations as evinced by the underground pipeline network of where the strongest intensity of ground shaking was in terms of its effect on the system. And when we do that, what you see here are the contours drawn for the average repair rate for the entire system. And we would know, for example, if we had 8,000 kilometers of pipeline and we had on the order of about 800 repairs in the cast iron mains, that we would have about 0.1 repairs per kilometer. We would have that knowledge, but we wouldn't know how it was concentrated in the system. So by doing this, you can see the concentrations of the damage. You can see that because we've picked a contour interval, which is the average for the entire system, that everything above that first contour line is above average, and the density of the contours are an indirect measurement of what the intensity of that system's response was to the earthquake. And then one can also then correlate these locations of intensity with subsurface conditions which affected this intensity. And what we'll see here in the Balboa Boulevard area are sands and interbedded clays and silts which are susceptible to liquefaction. The problem about having interbedded clays and silts and liquefiable layers is that pore water pressures generated by liquefaction tend to migrate to the impervious layers of the clay and create even a more slippery surface for soil movements to occur on. There's a location down here which is called La Cienega in Los Angeles. That means the swamp. This was an area that was subjected to strong ground oscillations because of softening sediments at that location during the earthquake with amplified dynamic movements and also caused some permanent deformation. But what I'm going to concentrate on is this contour interval over here and this location which says soft clay deposits susceptible to lateral movement and lurching. And as a result of this work that we performed at Cornell and also their own curiosity in the problem, Tom Holzer and his colleagues at the U.S. Geological Survey sent some crews in here to do some site explorations. And one of the first things they did, this is a location within that zone, is they plotted contours of displacement. You can see the ground surface here in terms of the topographical contours. And all the vectors of movement, of course, are about perpendicular to the contour line. So things are sliding down slope. These were vectors that they drew based on surveys that they had of the street prior to the earthquake and then resurveyed after the earthquake. And they could then deduce from that, by doing some manipulation of the vectors, some estimates of ground strain, which you see over here. What I'd like to do is to focus our attention on this vector, which is about the maximum displacement, but not, shall we say, a displacement not representative of the others. We'll notice that it's a little over 300 millimeters, so maybe on the order of about 35 centimeters or so. Their explorations disclosed, and this was what was truly astonishing because nobody could figure out why there was such a high concentration of pipeline damage at that location, soft clay deposits, normally consolidated clay, existing about 5 meters below the ground surface, just below the water table. These have now been attributed to overbank deposits from when previous historical flooding and prehistoric flooding occurred in this area. This is a semi-arid environment. You wouldn't necessarily expect to find soft saturated clays. And they only were able to put 4 borings down, and they hit the clay in 3 of them. So the possibility of this being rather extensive certainly is a reality. This soft clay, of course, has a low strength on the order of about 20 to 25 kilonewtons per square meter. So it has a strength which is weak enough that under the high pulses of acceleration, we may get deformation. So one can perform what we call a Newmark sliding block analysis of this, where one assumes that the soil behaves as a rigid material. It can slide if the accelerations which generate the inertial forces downslope exceed some yield level associated with the resistances which are acting against the downward movement of that block. And if one were then to define a yield level of acceleration and then define the dimensionless acceleration as the ratio of that acceleration that would give rise to movements downslope divided by gravity, then one could see that by integrating the areas above that yield surface or that yield acceleration line, one would get velocities, and by integrating velocities, one would get displacements. And so we took a record that was available through the record of seismometers that were deployed by the University of Southern California. There was one within 1 kilometer of that area. We resolved the displacements perpendicular to the ground surface at that, or the records perpendicular to the ground surface at that location. We calculated what the yield dimensionless acceleration would be. That's a function of the direct simple shear strength which is developed along the sliding surface, a passive resistance at the down toe end, an active resistance at the up toe end, and then a tangent of alpha indicating the orientation or the angle, which in this location was only about 1 to 2 degrees. The site looked like it was virtually flat. And what's interesting here is if we recognize that the relationship between the direct simple shear strength of soft clay, particularly normally consolidated clay, and the effective vertical stresses at the depth where we find it is anywhere from 0.22 to 0.3 is a favorite number multiplied by the overconsolidation ratio. We substitute that back into our expression over here. We actually can come up with a recognition that if this length of the slide is long, and it was relative to the depth, and the tangent of alpha is relatively small, that this yield acceleration is really related to overconsolidation ratio. And in fact, one can show that when overconsolidation ratios begin to get to values of 1.5, so lightly overconsolidated to slightly more than lightly to around 2, that the opportunity to generate significant downslope movement becomes severely diminished. This is that record which has been resolved in the direction of the slide by integrating these accelerations, double integrating them in the following way to get velocities and displacements. We actually came up with about 36 centimeters of downslope displacement, which was very consistent and close to what was measured in terms of pre- and post-earthquake surveys. You can take air photos and you can do pre- and post-earthquake analysis of those air photos, and you can, by doing photogrammetric measurements, get a map of the permanent ground deformation that occurred as a consequence of the earthquake. And in working with our Japanese colleagues, in particular with Professor Hamada of Waseda University, we did collect air photos. We flew high-quality, low-altitude aircraft to get stereo pairs after the earthquake. And then by analyzing those air photos photogrammetrically, we could evaluate the displacements of the ground. And this is showing you the displacements that were evaluated from those air photos in the vicinity of Balboa Boulevard. And what you see also here are sort of mauve or purple arrows, which were inferred displacements, again, by surface surveys that were done of the street before and after the earthquake. And you'll see that the air photo vectors are reasonably consistent with some of the survey data. And in fact, if we were to compare displacements that were given by the air photos and survey data in the location of this lateral spread on Balboa Boulevard, one sees the comparison. It looks like this. There is some disagreement, but overall there's reasonably good agreement between air photos, which do carry a certain amount of error in them, and the actual surface measurements that were made on Balboa Boulevard, so that we have some confidence that these air photos are giving us a good global idea and reasonably accurate one of displacement patterns. We then can take these displacement patterns and infer from that ground strains, draw contours of ground strains associated with permanent ground deformation, superimpose upon that the pipeline system and the repair rates, and then draw a correlation between repair rate and permanent ground strain in areas of ground failure. And this is showing contours of ground strain. We have compressive strains here where the pipeline was buckled, tensile strains here at the upper edge of the failure on Balboa Boulevard where it was pulled apart, a variety of different pipe repair locations in this particular area, and then a superposition on these ground strain color contours of pipeline repair rate here in terms of repair rate in terms of 5 repairs per kilometer, very heavily concentrated damage here. And one can then infer, and this is just the beginning of this kind of work, relationships between repair rates and ground strains that might look something like this. We also can take strong motion data associated with the seismometer information. This is color-coded in terms of various ground velocities. Ground velocity, for a lot of reasons, is a representation of ground strain. That is most directly correlated with the pipeline damage being a buried object. And if we now count the number of pipeline repairs within these contours, these color contours representing, let's say for here, an average of 55 centimeters per second velocity, peak ground velocity, we can get a repair rate that correlates with that velocity. And what you see over here are a variety of regressions that were developed, all having reasonable R-squareds that allow us to do better in loss estimation analyses for future earthquakes and future events that would generate velocities of this order. Talk now about large-scale tests of ground rupture effects on buried structures. And I'm going to talk about what, at the time, and I still think is, the largest laboratory experiments that were performed of ground rupture effects that was performed at Cornell with the support of the Tokyo Gas Company. And Tokyo Gas is concerned because they have a lot of what they call high-pressure gas distribution lines that go through Tokyo, and very many locations in Tokyo are subject to soil liquefaction, which can generate lateral spread. And as any pipeline in a crowded urban environment, it has to change directions relatively rapidly along existing rights-of-way, which are typically the streets. So you get a lot of 90-degree elbows or bends in the line, which are part of the structural feature. Sometimes they're 120-degree bends, or they may be 70 or 60-degree bends. But we looked at a 90-degree bend and the effect of permanent ground deformation that would affect the behavior of the pipe at that bend. And this is a picture of the test basin prior to running the test. Here is an actual pipeline shipped from Tokyo. It happens to be 100 millimeters in diameter. You can see the bend in this part of the box. This is one of my previous students, James Mason, who is standing in the box to give you some scale. The soil that filled these boxes was approximately 60 metric tons, and developing the means of moving that much ground and controlling it in terms of its dry density and in particular its moisture content, because we looked at these tests not only for dry conditions but for partially saturated conditions. And this provided some very, very interesting insights as a comparison between dry and partially saturated. So what you're going to see in the next slide is a video. What happens is that this is the stationary part. We designed the dimensions here so that the sides of the box were far enough away not to interfere with the interaction. And you're going to see this part of the box dragged to the left, or to the right, excuse me, to create a right lateral strike slip movement that might be existing at the margin of a lateral spread or be representative of a fault crossing. And it's going to move approximately 1 meter, so quite a large amount of displacement. So you can see the rupture occurring here where the actual displacement between the two boxes is occurring, and you'll see the fractures and cracks starting to emanate longitudinally along the pipeline. But if we replay this, I want to concentrate your attention down here where the elbow of the pipeline is, because in the distance you're going to see some manifestations of permanent ground deformation at the surface. And so the next slide is showing you from that angle. The elbow is in here, and you can see that it's stationary. It's anchored over here, and as the ground is moving forward, it's acting as a plow, if you want. The ground is settling on the far side of it and being heaved up in terms of a net passive resistance that's being developed in the ground on the other side. So if we look at the final shape, you can see that as this block or this basin has been moved from left to right, it's created this deformation, an inflection point in the pipeline, which we would anticipate. And we took all these tests to failure. The 1 meter was sufficient to fail the elbow in each case. The way in which we try to model this behavior, because a elbow is a shell, so we need to evaluate this as it is a thin-walled shell. And we use the program Abacus and combined shell elements with beam elements to represent long lengths of the pipe that would essentially behave as beam columns under this circumstance, and then connect these with PY relationships and TZ relationships and so forth to get the combined interaction between the soil and the structure, where here, by virtue of multi-point constraint, we weld our analysis of the shells to our representation of the pipeline not undergoing that three-dimensional deformation in terms of a beam slider, in terms of a beam column. And the way we were looking at the interaction here is somewhat a conventional means, but one which is, at this current stage of our technology development, one which is able to capture some of these large relative displacement effects between buried objects and the surrounding ground in the terms of PY relationships, or longitudinally in terms of TX and then QZ for the vertical. If we look at this as an extreme loading condition, we recognize that extreme loading of soil is accompanied most often by extreme loading of the structure, so that modeling the material and geometric nonlinearity of the structure is also necessary. And a series of tests were actually performed on these elbows. This happens to be a closure of the elbow in the direction of the 90-degree elbow. So this is 80 degrees, and interestingly enough, when you deform them in the closing mode, they don't break. They are ductile enough to withstand the deformation. Here's some of the hybrid model compared relative to the actual experimental data. But when you flex these in the opposite direction, so now instead of closing it like this, you press down to open up that particular elbow, they will rupture. And this is undergoing a change in angle of about minus 44 degrees, the change in angle being opposite to the positive angles that we saw before. So understanding these structures in terms of their nonlinear behavior and then coupling them together becomes important. This particular picture is in the paper. This is a comparison between the finite element analyses and the experimental deformations, which is quite good. There's a good comparison between strains. Some of the gauges under this severe condition of deformation became despondent before they got to the very highest levels of strain predicted by the finite element program. The principal results of this large-scale experiments were that it qualified and validated a hybrid finite element model that is used for Tokyo Gas in terms of their general engineering analysis, design, and siting decisions. They also learned that if they could increase the wall thickness in the vicinity of the welds by only a fraction of a millimeter, that actually increased the performance by over 200%. So that was a very dramatic and important contribution. And then we found that the pipeline strains were significantly higher in partially saturated soil to, as best we could establish it, similar densities than for the dry sand. So the next issue then is soil structure interaction during ground failure, and we did a series of experiments on partially saturated sand where we built a test compartment like this, took the pipelines over here, and pulled them laterally through the ground with soils both dry and partially saturated with 4 and 8% water content. Now you may ask why we only use 4 to 8% water content. Well, strictly speaking, if you're dealing with soil above the groundwater table, you should only put as much water as can be held within the interstitial voids. And with the densities we could achieve, any water content higher than about 8% just gravity drained in terms of partially saturated flow to a lower level. This is a representation of some of the soil, or what it looked like. And what we found this is a grain size distribution. This is a picture of the soil. And what we found is that if we ran, and we did a lot of these index tests, direct shear tests, to get a sense for what the peak friction angle was in direct shear. This plot over here represents the dry sand, and this plot over here represents the partially saturated sand, and we didn't see any difference between the 4 and the 8% moisture content, so that for a given dry unit weight, one sees an increase of about 4 degrees in terms of peak friction angle for just a little bit of water which is placed within the sand matrix. And if we were to look over to here, go to this slide, you'll notice that there is this distinctive upturning as we achieve certain densities both in the wet condition, or the partially saturated condition, and in the dry condition. And we ran a series of experiments where we could rapidly disassemble and cut sections through the direct shear specimens. And what we noticed is that this junction going from a ascending level of peak shear resistance relative to dry unit weight this accelerating point here, where it goes up at a much faster rate, is associated with small changes in density that are related to wedging of the smaller particles, like real door wedges, in between the larger ones, and literally locking them into place to have a significant larger asperity or interlocking aspect to them. It's quite remarkable, and it occurred at very dramatically for all the sands that we've looked at, and we've tested quite a few at a certain point in the dry density plots. We evaluated dry density with what's called the Seelig density scoop. This is a device that will, when the operator places it with a particular platform on the ground and applies a certain weight, these scoops go down, and the weight which is picked up in the scoop can be correlated to the unit weight of the soil, and then we can correct for moisture content and get the dry unit weight of what that soil is at that location. We found that when we got into the denser sands, and in particularly when we got into the partially saturated sands, they tended to be very dilative and very volume expansive. So what happened is, as the density scoop began to be pushed down into the ground, it tended to rise up, and we didn't get as much soil in there, and therefore it gave us a correlation for a lower dry density than we should have had. So we had to modify the testing process to provide enough anchoring force on that platform plate in order to make sure that that scoop wasn't moving, and we got an appropriate correlation between what was carried in the scoop and the actual density of the material we're trying to measure. And when we made these corrections, we've got this very, very nice correlation line in here, uniting both the dry soils and the partially saturated ones. The test results look something like this. At comparable levels of dry density, you have, for the dry sands, something looking like this, and for the partially saturated sands, a much more brittle behavior, higher initial stiffness, and most importantly, a significantly larger lateral maximum force. And if we were to compare the lateral force as a function of dimensionless depth, the depth to the center line of the pipe divided by its diameter, you can see in comparing this for the partially saturated, and by the way, the 4 and the 8% moisture contents were virtually indistinguishable. When we plot and compare these two, you're getting over 2 times the lateral force for this partially saturated situation. What is equally interesting is the geometric failure conditions associated with the partially saturated soils relative to the dry. In dry soils, there tends to be a flow of the drier particles around the pipe in a kind of a generalized surface of concentrated deformation. Whereas in the partially saturated soils, we even got voids that were, because of the apparent cohesion, opening up behind the pipe in a very distinct geometry of rupture occurring like this. So now that this whole thing was a weight that was now transmitted to the pipeline, causing greater lateral force. So there's some very interesting things going on here. In the small amount of water that was added, it is as if you were to go into a room that had a stack of chairs that were randomly distributed, and you were to push on those chairs and they'd fall over. And then you'd sprinkle a little bit of water in on those chairs, and you try to push them over again, but you couldn't get them to push over until you exerted twice or more of the force that you did before. 4% moisture content is a very little amount of water. It had not only an influence on increasing the friction angle for a given dry density, but most importantly, I think, it changes the geometric nonlinearities of the rupture surface, which then contributes to higher forces on the pipeline. So dry sand, partially saturated. And then finally, we developed a series of dimensionless curves associated with dimensionless depth, dimensionless force over here, where we could take the lateral maximum force, divide it by the unit weight and the depth to the center line of the pipe and the diameter of the pipe, and that should be an L, and I've got that as an H. So if you make that an L, we'll be all set. And what you can see here is that there is a significant difference between the dry and what's predicted for the partially saturated soils. I'm going to talk about, for just a minute, this national earthquake, this network for earthquake engineering simulation, where there are a number of institutions, and I understand there's a project here involving the University of Texas facility. Cornell has one, and we are currently planning and have built a facility to do these kinds of tests. This is a picture of it, and what you see here is a low reaction wall. This is anchored into the floor of our laboratory with the 28 rock anchors to get the necessary vertical tie-down forces for the lateral forces that are going to be acting on these split boxes. We have these long stroke actuators that can generate not 1 meter of displacement, but 2 meters of displacement. And we have some external testing frames for looking at biaxial states of stress in pipelines above the ground. We also built our soil storage bins into the wall of the building. We have structural columns here which are intended to provide lateral force for experiments. So they're quite deep. They're about 3.5 feet deep. There was a lot of dead space between them, so we created these storage spaces. They can store about 100 metric tons of sand. They don't take up any floor space, whereas we used to have a 3-story storage bin for the Tokyo gas tests. These are completely recessed into the wall, got guillotine doors here. We have a system of customized conveyors that can put it up in the top and take it out of the bottom and move it all around. So we also have a high reaction wall for above ground facilities. And then, of course, this displacement, and we're currently just about to perform what will now become the largest full-scale experiments of ground rupture in the lab, where we're actually going to be moving about 100 metric tons of ground with high-density polyethylene pipelines of 400 millimeters in diameter. These are big pipes. We work in conjunction with the RPI centrifuge. Their 150 G-ton centrifuge allows them to scale down dimensions. So we can look at the interaction between the buried structures and the extreme loading of the ground in some great detail, but we are limited because to try to move more than 100 tons just gets to be too time intensive for the personnel that are involved, and I would wager that that becomes economically and time-wise inefficient. However, by working in conjunction with RPI, they can speed up gravity. They can, in a smaller scale, get the effect of lengthening the pipeline so that they can, where we can look at lines that might be on the order of 20 meters long, they can look at things that are on the order of 180 meters, and then we can do things at the boundaries to simulate the behavior of the pipe beyond those levels. But our facility is geared up so that we can look at the interactions in permanent ground rupture where most of the action is occurring, where you get most of the curvature and change in the pipe. And here's some of the split boxes in the RPI centrifuge. They've since fabricated and have several others. And then we have currently a comprehensive program to look at various ground rupture patterns, be they strike-slip, imposing tension or compression in a crossing line, or a normal fault, a subsidence-generated type of abrupt ground rupture, or a compression-generated abrupt ground rupture. We have created a matrix here of 60 different cells with all sorts of variations in these ground rupture patterns, different kinds of pipelines to be studied, and then these cells are populated either with tests at Cornell, collaterally with RPI, or singularly at Cornell and singularly at RPI, and then the rest are numerical. So we have about 20% of the cells anchored down with full-scale physical experiments, and the others would be populated with numerical that are not that far in extrapolation off of the physical, and that allows us then to develop a comprehensive database and library of permanent ground deformation effects on buried structures. So that brings us to my final, or shall I say penultimate slide, where in looking what I've tried to present is I've tried to say that extreme loading events are important, and they are important both at the component level and they are important at the system-wide level. And I think one of the most exciting areas to work in is understanding how components affect system-wide performance. And so I have a few slides here to illustrate to you how we take this component behavior and carry it forward into a system-wide evaluation of performance for the water supply in Los Angeles. We have created for LADWP, Los Angeles Department of Water and Power, through multi-scale modeling, a very, I believe, accurate representation of all 12,000 kilometers of their pipeline that we can subject to a variety of earthquake hazards. We have empowered that program with a special hydraulic network simulation model that works on highly damaged systems. Your off-the-shelf hydraulic network model cannot do that. It will solve for heads in the system that preserve continuity of flow, which means you'll be getting negative pressures in a system that can't sustain those negative pressures. Ours will not do that. We'll get an accurate representation of the flow under conditions of pressure that can actually exist. It accounts fully for soil structure interaction, and we've done probabilistic seismic hazard analysis to capture the regional seismic risk, and the whole thing is tied into a GIS system because when we look and make decisions on these complex systems, we need to visualize them. This is a representation of one of the earthquake scenarios and its influence in terms of peak ground velocity on the LADWP system. This is associated with the Veridigo fault system. And this is a representation of the behavior of the system after we've simulated it for this one particular scenario, and that gives us a number of nodes which no longer are serviceable. We can take the nodes in the system that can't supply water anymore and divide that by the supply that could be provided before the earthquake, and we get what's called a system serviceability. That is, there's only an 81% capacity of that entire system to provide water where it needs to be provided. And one then can develop system risk curves. We, of course, for every earthquake scenario we look at, do a Monte Carlo simulation with multiple runs to come up with statistics associated with what those outcomes are. We've worked with URS and LADWP to come up with a seismic hazard evaluation predicated on 59 earthquakes. We call them the scenario earthquakes, which are representative of the aggregate seismic hazard, and they've done some analyses to show good compliance for the entire Los Angeles region, which would then be subjected to a lot of different potential earthquakes. And then we develop this annual frequency of exceedance relative to system serviceability, and you can see that for our lowest probabilities and our most severe events in some instances, we can get down to serviceabilities on the order of about 75%, increasing in terms of probability as we go back up. And what you can see, if we now divide the system up into its major 5 components, so we have the West Valley, East Valley, and San Fernando Valley, the western, the central, and then the harbor section of the system, and do the same kind of serviceability risk curves, you can see that clearly the harbor system is the one, given the aggregate seismic hazard for Los Angeles, that's the most vulnerable. I think when you look, you can see with these narrow corridors here, losing a couple of the major lines coming down here can have some very serious consequences. What this allows us to do then is to look broadly at the system in terms of multiple hazards and threats, come up with a quantification for decision-making purposes, and also to have a library of scenario earthquakes so that the engineers can study some of the specifics about how the system responds under various circumstances to go in and evaluate the repercussion of these component behaviors. By the way, what we also can do in this system is to put in an improved component, put it in 100 times as it would be being used and replacing older not so good functional components over a period of time to see what the improvement in the system serviceability is, and therefore have a probabilistic means of showing what the increase in reliability is from an increase in component behavior. So it's really from the component sand grain size to the component size to the system in terms of the evaluation and analysis of infrastructure. And then finally, I'd like to end this particular talk with a quote from T.S. Eliot. T.S. Eliot in the four quartets has a quote from one of the 4 poems called Little Gidding that says, "We shall not cease from exploration, and in the end of all our exploring will be to arrive at the place we started and to know the place for the first time." I think engineering is a cyclical process where we look at things at scale, small scale, medium scale, large scale, and then return to the small scale. And every time we iterate through this process, we perform an exploration and arrive where we started. We understand the intricacies and the practical ramifications better. And so I'll end this lecture where we started, in Los Angeles, the home of Arnold Schwarzenegger.
Any questions for Professor O'Rourke? No questions? I was happy to go ahead.
We heard that the Texas A&M students were very, very good, and I'm really glad that everybody got all the points that I made.
I was very happy to see that you have a great balance between experiments and numerical simulations. A fairly high-ranked official at the National Science Foundation told me reasonably recently that in the relatively near future, we would not use experiments anymore, that everything would be simulated and that there would be no need for experiments. How do you feel about this, considering the time and effort you're spending on experiments?
Every time I run an experiment, and of course they have to be intelligent experiments, we have to have a question that we want to have answered, I am amazed at what I find out. It is absolutely a revelation. You know, one of these was the fact that at one point we were trying to simulate these high-pressure water lines, which are joined together by what they call a welded slip joint. It's a circumferential fillet weld. And we were combining one section of pipe with another section of pipe with what they call multi-point constraints in abacus, which joins everything together just as you would figure a weld would do. But the problem is we weren't putting the weld in. And when we ran the experiments with the actual welds in there, which are thicker than you think they might be, the actual mass of that weld was butting up against the curvilinear portion of one part of the pipe and actually precipitating the buckle much earlier than was predicted with the prior model. And so that large-scale experiment told us we've got to model that weld and put a lot of energy into characterizing its geometric shape, getting it accurate, putting it in the location where it's actually installed in the field. And lo and behold, when we did it, without any further adjustment, the analysis results fell right in line with the actual experimental results. Without experiment at a scale and a directedness to the question that you want to ask, you can't believe your models. I mean, you have to have them validated. So what I would say in response to the high official at the National Science Foundation is that to move forward to the next generation of models, we have to validate the current one, and then we can extrapolate only so far based on what we've been able to validate. Yeah. But once we stretch that application farther than would be reasonable on the validations, then we need to look for the next plateau of validation to expand the model further. And I think that hand-in-hand approach is an absolute must.